So you see on the screen, the probability of type 1 error is 0.0027. So again, recall, okay, try to recall how to get this 0.0027. This value 0.0027 is called probability of type 1 error. So in control chart sense, this value 0.0027 represent the probability of what does it mean? Probability of what? Yeah. On the screen we see probability of type 1 error. But what does it mean actually? So it means this is the probability. Yeah, if we use the simple word, we might say the probability of a point. Okay, the probability of a point outside of control limit. Okay, you get what I mean? I repeat, this probability of type 1 error means, the meaning of this probability of type 1 error means the probability a sample point is outside of control limit. It means that in a control chart, the probability of a sample point is outside the control limit is 0.0027. So when I say outside of control limit, it means that the point can be greater than upper control limit, or the point is lower than, or no, the point is less than lower control limit. So in the other word, the point is not inside the region of control limit. When we say inside the control limit, it means that the point is located in the region from lower control limit to upper control limit. So in that region. If you refer to the control chart at the bottom, yeah. So the first line and the last line, okay, the first, you can see 1, 2, 3, 4, 5, 6. No, 1, 2, 3, 1, 2, 1, 2, 3. There are 5 lines here. So the first line and the last lines are the 3 sigma control limit. So when we say outside of the 3 sigma control limit, so it means that the point is greater than 1.7, or the point might be less than 1.3. This is called outside of control limit. Then for the terms, we said inside the control limits. So it means that the point located in the region from 1.3. Okay, 1.3 is the lower 3 sigma control limit. Okay, 3 sigma lower control limit, 1.3 to 1.7. 1.7 is the 3 sigma upper control limit. So this is called in, okay, in the control limits. And last meeting, we have mentioned about this warning limit. Before that, let's see the probability limit. Type 1 error probability is chosen directly. So we have mentioned many times the type 1 error. So type 1 error, the value of type 1 error actually represents the probability. What is the probability of? What is the probability for the type 1 error? So these type 1 errors indicate the probability of, if we consider the hypothesis, this is the probability of reject H null, right? Reject H null, but H null is true. It means that we accept the wrong we accept the wrong information. Right. We reject the true one, but we accept the wrong one. Yeah. Type 1 error. We reject the wrong one. No, we reject the true one, but we accept the wrong. We reject the true. Okay, we reject the true one, but we accept the wrong one. So this is the type 1 error. We have discussed for 0.001, so how to know the sigma control level. So just refer to statistical table 0.001. Yeah, so make sure you know how to read the table. The table I show to you is the same for the statistical table provided during in final exam. So I think not a problem if you're familiar with the statistical table. Yeah. Statistical table, okay. So just now we have mentioned 0.001. So we refer to this statistical table. Make sure the value give us the right hand side value. So all the value in this table tell us the probability or the area under the curve at the right end tail. So 0.001. Yeah, you can see where is 0.01. Here, right? 0.001. Okay, 0.001. So this is the probability value. Then what is the z-score? Yeah, in the statistic we said z-score. What is the z-score? So you read along the row. Okay, along this row is 3. And then you read along the column 0.09. So 3.09. Okay, I repeat. Refer to 0.001. So you read according to row, which is 3. Yeah, you can read through along this row. So you get 3.0. And then you read along the column, you see 0.09. Okay, 0.09. So 0.001 is given by 3.09. Okay, z value or z score is z score is 3.09. But in quality control, this one we need to alert because sometimes the same the same notation have the different meaning or have the different names. Just now I have mentioned to you, yeah, in statistics, we say z score. For 0.001, z score is 3.09. How about in quality control? In quality control, when people said z score, actually this z score is referred to sigma level. Okay, you see, one is z score, one is sigma level. So in the different field or in the different area, they have the different names, but actually at the end they are the same things. You know what I mean? So I repeat, 0.01, this is the z score, 3.09. In quality control, we said 3.09 is sigma level. So this is one thing. Okay, this is one thing, different meaning or different name, but actually refer to the same things, same item. Another one is alpha, right? Alpha, I have mentioned to you alpha. First time you see alpha is in sampling, no, in hypothesis testing. First time you see this. alpha from type 1 error. Then after that, we know this alpha actually represents the probability value. And then after you have taken statistical inference, then you might notice that alpha have others meaning. Confidence level, right? So this thing we need to understand, and we try to link with them. So if people say Z-score, so in quality control, yes, we might say this is a sigma level. In other area, let's say in factorial design, alpha equal to 1. I think you have many statistical friends, when they do some statistical research, they say, oh, you see p-value. P-value is equal to 0.05, okay, significant. So this p-value actually also refer to alpha value. Okay, now I'm back to okay. Now we see warning limit. So this warning limit typically selected as 2 sigma limit. Okay, this is for typical case. If 3 sigma control limit, then what is the 2 sigma limit? So from the figure, okay, from the control chart, figure 5.8, I have mentioned to you, this warning limit tell us that there might something happen in the process. Something might be want to be happen. Something might happen but not happen yet. It's just from the data we collected. Then we might sense, or we might feel that, or we might observe that something might happen in the process but not really happen yet. If we can see from the control chart and we observe that there are many points are located around warning limit. They say there are many points around 1.6342. Okay, around. Or there are so many points around 1.3658. So these are 2 control limit for warning limit. So if this situation or this pattern happen, then we have to alert that something might happen. It's better we have to take action rather than something have already happened in the process. Because if something already happened, let's say we notice that there are so many points, there are so many sample points outside of 1.7013, 1.2487. So there are so many outside of these 2 control limit, 3 sigma control limit. Then the situation might be worse because we need to rework. Maybe we need to rework. Maybe we need to reproduce, or we need to repurchase. So this is refer to the basic of control, quality control. In the beginning, in the first chapter, we have mentioned the definition, and then we have mentioned the modern definition. We also have mentioned the specific terms like improvement, like waste, like variability. So this thing might happen if we have noticed that many points are outside of control limit. Now, of course, as control is as a QC or as a QE, we really don't want to see so many points are out of control. So in statistics, they say outlier. If there are so many points outside of control limit, outside of the 3 sigma control limit, so they might say outlier. So in quality control, we also can use the term outlier. So we understand this outlier actually refer to the point outside of the control limit we concern. So in our discussion or in the slide, always we see the control limit, 3 sigma control limit. Why always we see 3 sigma control limit? Because in industry, normally they use 3 sigma, okay, 3 sigma label. but not necessarily all. I mean, not all of the industry or not all the company use Three Sigma level, but just for majority. Okay, majority of them use Three Sigma level. Some of the company might use Four Sigma level. Some of them might use Six Sigma level. So it depends actually. Yeah, if one day you'll be QC or QE, yeah, maybe you can notice which Sigma level is used in the company you serve. And sometimes we can consider the Sigma limit, either we increase or we decrease for the quality improvement purpose. Okay, this one I have mentioned to you, right? If sometimes we cannot do something, or we cannot improve the process. Okay, sometimes if we cannot improve the process, what can we do is either we increase the control limit. So we have discussed, if we want to increase the control limit, what shall we do? We have to consider the lower Sigma level, isn't it? So Sigma level increase, control limit will be reduced. This one I have showed to you last meeting. So as QC or QE, not necessarily just read from the slide. Okay, not necessarily we just read from the slide. The information in the slide just give us a basic. I don't think you can find this information as I showed to you last meeting. Increase Sigma level, then control limit will be reduced. No, right? You don't see this information from the ebook. But we as mathematician, or we as QC or QE, we should alert this thing. Okay, we should alert this thing. If we know this thing might happen, control limit increase and then Sigma level reduce, then this is our advantage, because we can refer this information when we want to do some adjustment, when we want to maintain, or we want to make some policy, especially in productions policy, what to do to remain or to improve the quality for the product. Okay. Any question regarding to what we have discussed last week? Yeah, actually we have discussed many things right in the last week. Data point. So simply to say, quality control is not the difficult subject. It's not the difficult course. Actually, this quality control is an extension. Okay, quality control is an extension of data analysis. Actually, we play with data. We go to production line, we collect a set of data, we do the sampling, and then we also have discussed it. Actually, this control chart, okay, the control chart actually is, we say, control chart represent the hypothesis test. So we have H naught, mu equal to mu naught. This is for the sample mean. So when talking about the hypothesis test, not necessarily the sample mean, we also can consider the sample standard deviation. Yeah. In quality control, we focus on the variability. So for this variability, how to measure? Just measure mean of the mean, or mean of the process, actually is not enough for knowing the variability. We also need to consider, for example, variant, covariant maybe, or we also need to consider, does it have any correlation? So this thing we have learned in data analysis. In last meeting, we also have discussed some of the reason why the control chart is so popular. Why they want use to control chart? Why Professor Schuhart proposed the control chart, and then after that, many industry they also follow. They use the control chart in representing or in investigating their process. Is it possible we can propose tools, other tools to replace control chart in future? This one I don't know, but maybe you can explore, you can try to think. Maybe you find that, yeah, this control chart is not so good, you want to improve it. So I want to tell you in our course, we just discussed a simple control chart. So if you go to research area, so actually there are so many control chart. The researcher or even the QC in QE or even professor, they have made some research or they have proposed a new control chart. Even you can read from the ebook, I think chapter 8 or chapter 9 in ebook. They call what they call, I can't remember. It's some S, start from S. I think we have mentioned. Then maybe we can have a look. What is the name of that? Q-sum. You see in chapter 9. Cumulative sum and exponential weighted moving average control chart. So this is others. I mean, this is the improved. This is the improved or modified control chart, but not in our syllabus. But if you're interested to know, then you can explore. Okay, you can explore this Q sum and another one is E what? This one EWMA control chart. So these two control chart actually is very interesting. So if you go to Google search, you search in Google, you find some research article. So you will find that there are so many type of control chart in the journal or in the literature. Not only for the control chart we will learn. Not only the Q sum or EWMA control chart. There are many. Okay, there are so many type of control chart. Maybe one thing you need to alert or you need to observe or you need to know when one day you become a QC or you become a QE, then maybe you need to know what is the current control chart the company you serve they use. Maybe they do not use the S-bar and R-chart, they might use Q-sum control chart. Yeah, I'm not sure whether you have read through chapter 3 and chapter 4. So information in chapter 3 and chapter 4 are the basic for us when we go detail. When we go to next chapter, control chart. Because many probability information will be used. So that's why I suggest that you have to read through or just go through or just have a look chapter 3 and chapter 5 and chapter 3 and chapter 4. Because sometimes when we mention some concept of statistical concept or the probability concept, hopefully you can understand. Okay, if no question from you, then we go to the next part. We call sample size and sampling frequency. Again, this is the extension from the sampling theory in the probability in the course of in the statistic and probability, right? Yeah, in first year you have taken right this subject, statistic and probability. So this is the extension. So after learning the sampling theory, after know the point estimate, after we know the sampling, after we know the hypothesis testing, then now we will apply the basic knowledge of sampling we learn in quality control. So first we start from sample size. So if you still remember, sample size is the number of point we taken in a sample, or we said the number of point in a group. So the group refer to the sample. It's a group of, or we say it's a collective data in a group. Okay, sample is a collective, is a group of collective data. Okay, this is the sample. Sample size, we can define sample size as the number of element in a group, or the number of element, or the number of data point in a sample size. So what is the relation, or what need to know about this sample size? So there is a specific terms in quality control. On the screen you can see average run range. Okay, average run range. So this average run range, there are two types. So what you see on the screen, the formula or equation given by 5.2. So this is called average run range. Okay, average run range, ARL, equal to 1 over P. P is the probability that any point exceeds the control limit. Okay, probability that any point exceeds the control limit. So in the other word, the possibility, this P is the possibility, a point outside of control limit. And this equation, ARL equal to 1 over P, this equation is used to evaluate the performance of the control chart. You know the performance? So when we're talking about the performance of a control chart, then we refer to this average run range. But what actually this average run range tell us? You refer to the ARL is the average number. Okay, ARL is the average number of points that must be plotted before a point indicate an out of control condition. So this ARL tell us that the number, or we say the average number of the point we should have before we can notice a point outside the control limit. So you might feel that so amazing, right? Mathematics is so amazing. How to know this thing? How to know the average number of point before a point is out of control? Yeah, before we go further, you just have a think, just think about it. How to know? How to know? How to know the average number of point before a point is out of control? Maybe we start from, okay, let's go to production. Let's collect a set of point. Let's say we collect 10 point. So what is the probability a point is out of control? It means outside the control limit. I don't know, can you imagine or not? We collect a 10 point. Can you imagine? Or what? Or we do some simulation from Excel? UCL, UCA, UCL. OCL. We do the simulation. Yeah, we take a simple one. See center line. So center line would be the line in the middle. So it's 1.5. Sample. So this is the sample. Choose a point. And randomly choose a point. Yeah, if I do like this, of course, all the point I've taken will be inside the control limit. See? Okay, we take 10 minutes to see how about this simulation. So if I take a sample with, okay, sorry, I have to do something here. So let's say I take 6 points. So if I use a command random between, then of course, all the points I consider, they are inside the control limit, isn't it? If I have specification, upper specification limit and lower specification limit. So this upper specification limit, let's say, yeah, the value USL should be greater than UCL. So let's say 110. This one, 30. Okay, now it's different, right? I take another set. You see, you might notice that some of the point. So in this sample, so this is the first sample. Maybe I put here sample 1. So in this sample, I have 6 points. And from this point, you may observe that how many points or how many value are in the control limit. All are in control limit, right? What if I have two samples? The number in these two samples still in the control limit. Okay, still have any point in the control limit? No, right? You see 103 out of control. You see anyone? No. We notice that 103 is out of the control. So I just provide you some idea, because we do not go to production line. Then how to understand this ARL? So from our discussion, we can set P. Okay, we can set the P with the 3 sigma level. So we already understand that. We already understood that for 3 sigma level. Okay, for the 3 sigma level, P, the probability that any point exceeds the control limit is 0.0027, isn't it? Then we can do the calculation like this. Yeah, notice that although from the previous, from equation 5.2, ARL equal to 1 over P. But in the discussion or in the application usage, this ARL can be divided into two. One is ARL not, or ARL 0, like what you see in the screen. ARL 0, subscript 0, or ARL not. Yeah, normally we might read it as not, H not, H1, right? So the same thing happened here. We have ARL not. Then of course we have another one we call ARL 1. Okay, let's see ARL not first. So just now I have mentioned you 3 sigma limit. So P is equal to 0.027. Yeah, remember this P value is the probability that a single point, fall outside the limit when the process is in control. Okay, process is in control, but we still can, but there is a possibility a point outside of the limit. So this possibility is measured or is given by the P equal to 0.0027. And this P equal to 0.0027 is actually come from 3 sigma level, from the sigma level we use. If we want to change, let's say, I don't want to use 3 sigma level, I want to use, let's say, 2.5 sigma level, then of course, P value will be changed. Then how to get the P value for 2.5 sigma level? (2.5 sigma level. No, not this value. You see, 3 sigma level, also not this value, right? 3 sigma level, so the value you see in the statistical table should be multiplied by 2. So we just do some division for 3 sigma level. So from here, 3 sigma level, 0.00135. So this value, 0.00135, we have to multiply this value by 2. Okay, multiply it by 2. So it will become 0.0027. So the same thing, if I change it to 2.5 sigma level, 2.5 sigma level. So what is the probability? What is the P value? So you take 0.0621 times 2. So it's 0.01242, right? 0.012 times 2, 1242, 0.01242. So this is how to determine the P value. How to find the P value from the statistical table. So you can see the information of P value is important in determining the ARL. Okay, now come back to 3 sigma level, 3 sigma limit or 3 sigma level. P equal to 0.0027. So remember the meaning of this P value, probably a point fall in outside the limit. So 0.0027. So from what we see on the screen or from the sentence, so actually we also can know the probability a point fall outside the limit when the process is out of control, right? The process is in control. We also can consider when the process is out of control. We also can consider the probability that a single point fall inside the limit when the process is in control. So I have mentioned you two terms. So just think of it, how to find the probability. Okay, come back to what we have discussed. So find the average run range. So the average number of the point, I also cannot remember. Average number of point that must be plotted before a point indicate an out of control condition. Yeah, so this is the meaning of ARL. So from the calculation, we get 370. So it means we have to understand the meaning. As mathematician, yeah, calculation is our strength, but can we interpret the answer, or can we interpret the result after the calculation? So we have to make it balance. We can calculate, we can interpret. Okay, now I believe that you can do the calculation. Of course, the condition is we should know the formula, or we should know the equation. Okay, so from the calculation, yeah, I suggest that you have to press your calculator right now to feel that this is how to calculate ARL naught. And then we get 370. Remember, the process is in control, but the possibility of point out of the control limit or outside the control limit is 0.0027. So after the calculation, after we calculate the ARL, so it means that although the process is still under control, is still in control, but out of control signal will be generated. What does it mean? From the control chart, we cannot always make sure the data point must be inside. We cannot control it. Maybe you say, sir, you said we can enlarge the control limit. If I find that 1 or 2 points outside the control limit, it's okay, I just enlarge the control limit. And this issue I have mentioned to you, we cannot suka in enlarge control limit, isn't it? Because this control limit, lower upper control limit, actually are calculated from the mean of the mean, from the sample, from the sigma level assigned, or from the sigma level fixed, because different company, they have different sigma level as a standard. So we cannot suka, there are 2 points outside of control limit. Let's say 1 point is lower than 0.5 LCL. Another point is greater than UCL 1.5. Okay, enlarge, make it UCL, make it to be 2, so that no point outside. So all of the point inside. So we cannot suka change it. So now come back to this 370. So this 370, it means that we collect the data, we do the sampling. So we collect until, or we do the sample, we consider the sample until we have we have collected 370 samples on the average, then we might get an out of control signal. Okay, again, you can see so amazing the mathematics, especially in this area, control, quality control. Maybe you might ask, sir, we collect the data, we plot the control chart. When you see, for let's say I collect 20 sample, okay, no out of control, all are in control. I collect another 20, become 40, still under control, no out of control. So people might ask, or QC or maybe junior QC might ask, when an out of control signal might happen. This is what this is what I have mentioned to you. The control chart, when we plot the control chart, we cannot make sure every time we can get the in control. We cannot make sure, okay, we cannot make sure the control chart we plot always in control. We just do know when, okay, we just do know when we will find 1 point out of the control limit. So we do know, right? But from the calculation ARL not, then we can calculate. So this is just a calculation, just a suggested number of sample to get an out of control signal. So it does not mean that we have to collect 370 sample just get one out of control signal. It tells us that this ARL tells us that on the average we have to collect 370 sample. Only can get one out of control signal. But this is the possibility. So maybe you collect until 300, you already get one out of control signal. Not necessarily we take until 370. Maybe we take the sample until 50. Until 50, we already get the out of control signal. As long as refer to the p-value, calculate ARL naught, then the value of ARL naught tell us the average number or average number of the point when an out of control signal happen. So I repeat one more time. So these 370 samples, we have to take 370 samples just to get one out of control signal. Okay, just to take an out of control signal. So this is easy to answer the question. When an out of control signal happen, you do the calculation, you answer with the value of ARL. So different p-value will give different ARL naught. Okay, you can read through. The use of average run range to describe the performance of the chart has been suggested to criticism in recent years. Then the reason why we use it is because the distribution of run range for a Shewhart control chart is a geometric distribution. There are two concerns with ARL. First, the standard deviation of the run range is very large. Second, the geometric distribution is very skewed. The mean of the distribution is not necessarily a very typical value of the run range. So these are two concerns with ARL. We can do some calculation using the geometric distribution. So that's why I advise that you have to read chapter 3 and 4 for the statistical distribution. So here you see geometric distribution. So do you know about geometric distribution? What is the mean? How to calculate the expected value? How to calculate the variance? So from the screen, you see there is a formula, sigma 1 minus p, sigma no, square root of 1 minus p over p. So this is the formula we use to calculate the standard deviation of the geometric distribution. P equal to 0.0027. And the standard deviation for this geometric distribution is, you see, we find the same value, 370. So means that the standard deviation of the geometric distribution in this case is approximately equal to its mean. So what is the mean? The mean, okay, the mean, the mean of the geometric distribution. How to calculate the mean of the geometric distribution? 1 over p, isn't it? So the mean and the standard deviation are the same. So is it only these features for geometric distribution? Do we have any other features for geometric distribution? Does the geometric distribution normal or skewed? If skewed, it is right skewed or left skewed? These are the sequence. These are some questions we might ask when talking about the statistical distribution. Okay, and in the last few sentences mentioned about the percentile, 10 percentile, 50 percentile. So for the 10 percentile, so what is the ARL? So already mentioned 38, 10 percentile. Okay, for P, for the geometric distribution with P equal to 0.027, 10 percentile of the distribution is 38. For 50 percentile, we have to understand what does 38 means? What does 356 mean? You can have a read. The last sentence, I think, yeah. This means that approximately 10%. So this 10% refers to 10 percentile. So this 10% of the time, the ink control run range will be less than or equal to 38. Okay, so 38, 38, 300, 256. So these values are referred to the average run range for different percentage. So ARL not for 10 percentile, 38. ARL for 50 percentile, 256. So this value, including 370, are referred to the average number before an out of control signal happen. We also have another formula. This is called average time to signal. Just now we mentioned about if we collect a set of, we collect a sample. So which sample, until which sample, then we can get an out of control signal. So calculate ARL. So for P equal to 0.0027, so 370 sample. Okay, from 370 samples, we will notice an out of control signal. But another question we might ask is, when does this 370 or when does this out of control signal might happen or might be detected? Then we can calculate by using equation 5.3. ATS equal to ARL time H. ATS, average time to signal. H, hours. These hours, not just simply a hours. This is we should say period, time period. You get the first sample. Then what is the gate? We want to take the second sample. So that is the duration, okay? Duration. So by using 5.3, we can calculate every time when this out of control signal happen. So just now this equation tell us the average number of point. This equation 5.3 tell us when every time, okay? Every time is when is the out of control signal happen. Okay, go through. The first two lines consider the hardware process discussed earlier. We suppose we are sampling every hours. So from ATS, we will have a 4 alarm about every 370 hours on the average. So you see, in our calculation, in our discussion just now, ARL 370. If we do the sampling every hour, we start from 9 a.m., we pick sample. After 1 hour, take another sample, and then 10, 11. So the gap is after 1 hour. Okay, the time period is 1 hour. After 1 hour, take the sample. After 1 hour, take the sample. So when we can get an out of control signal? After 370 hours. So one is the quantity, another one is time. Another thing I have mentioned to you, ARL1. Just now we have discussed ARL0 or ARL1. Then how about this ARL1? Suppose we are using a sample size of n equal to 5. When the process goes out of control, the mean shifts to 1.725. From the operating characteristic curve, you can refer to figure 5.9. We find that if the process mean is 1.725 microns, the probability of X bar falling between the control limit is approximately 0.35. This is another probability I had mentioned just now. So you see the formula for ARL, not the formula for ARL1. The same, right? 1 over P. But the P value or the probability, the meaning of P might a little bit different, right? Do you see any difference? Have different or do not have any difference? Probability of X bar falling between the control limit. So this is P, right? P equal to 0.35. But just now we also have mentioned P. Okay, refer here. P 0.00227, probability that a single point fall outside the limit when the process is in control. Process in control, but point outside of the control limit. But for ARL1, probability of X bar falling between the control limit. You should see something different, right? Although the formula is 1 over P, but the meaning of P a little bit different. In ARL, P is equal to 0.35, refer to the probability of X bar falling between the control limit Just now the point is outside the control limit, but now X bar falling between the control limit. So maybe you need to highlight the terms so that you can see the difference and you can use the right information to calculate either AR0, L0 or AR L1. Okay, to calculate is it's not difficult, it's very simple. But can we interpret AR L1 2.86? What does it mean? The control chart will require 2.86 samples to detect the process shift on the average. Just now ARL0, the mean, the value of mean still remain the same at the center line. Center line do not move, do not change in ARL0. But in ARL1, because outlier exists, okay, because existing of outlier might change the center line. I'm not sure you understand this information or not. Maybe we can have some simulation. Let's say I have a set of points. Okay, I have a value from 100 to 200. Let's say we take 10 value. Okay, I have 10 value here. So this is a sample. In this sample, I have 10 value. What is the mean? Average. And you notice that the value less than 200 and more than 100. The value very close to 100 is 105. The value close to, the maximum value. Yeah, maybe we find the maximum value first, so that you can see, you can agak-agak upper control limit. So agak-agak maybe upper control limit might be 180. Why I said 180? Is it possible 176? Can, as long as the value greater than maximum value, then the process is in control. And then for the minimum, $105, right? Yeah. So for maximum and minimum value, we can agak-agak. Of course, we don't want to take upper lower control limit, upper control limit equal to 175. We don't want to have the point actually or located at upper control limit. So we should consider the value greater than 175, so that the maximum point still in control, still inside, still in the control limit. So the same thing for minimum. We don't want to take the point exactly located at the lower control limit. So we don't want to take 105 as lower control limit. So we might take 100, right? Okay, now we find the mean. It's average. Okay, we find the mean. So the average value will be 140.2. Okay, 140.2. So the mean is, if we're talking about the center line, so from what we have, center line can be this value, right? Okay, center line, we can consider this value. Upper control limit. As I said, we don't want to keep 175. We consider one value greater than. Maybe I take 180. Lower control limit. So don't confuse about the value. It's just for discussion purpose. But in logic, okay, in logic, what I mean here is for this 10 value should in the control limit. So inside the region from 100 to 180, but both endpoint 100, 180 are not included. So this is what I mean. But when we're talking about the mean shifted, the mean is shifted. This is happened when we consider ARL1. In ARL, no other shift. The mean still the mean, won't change. Then why the mean can move, or why the mean can shift to other value? Let's say there is a sample, there is a value more than or outside 180, greater than 180 or lower than 100. Let's say this value 110 is not 110 but is 210. Not 110 but 216. Not 116 but 216. So do you notice something? Yeah, maybe back. Okay, you look at this value, mean and center line. First, for this 10 value, they are located in the control limit from 100 to 180. Let's say, now, there is a point greater than 180. So let's say this 116 become 216. So do you notice? The mean, originally it is 140.2, right? But because 216, this value, okay, because 216, the mean shift, okay, the mean of just now what is the value? 140. Okay, just now the original mean is 140. Yeah, because we have 216, this value make the mean of 140.2 shift to 150.2 because of 216, and you notice that this 216 is an outlier, where we say this outlier or this value is outside, is not in the control region, or it's not in the control limit, it's outside of the control limit. So this is what happened. The mean shift from the mean of 140.2 shift to 150.2 if the value greater than upper control limit. What happened if lower than lower control limit? No, I should say smaller than lower control limit. Let's say 60. So you see, 16 is smaller than lower control limit. And then the original mean of 140.2 will reduce to 130.2. So there is a changes. Okay, there is a change of mean, or there is a change of center line's value. Then we say this is a mean shift. The mean shift from 140.2 to 150.2 when the value greater than UCL. The mean shift from 140.2 to 130.2 when the value or data point smaller than LCL. Okay, you get what I mean? Yeah, we have to really understand these two situations, because when we calculate ARL0, when we calculate ARL1, you notice that the formula 1 over P, yes, we use the same formula 1 over P, but the meaning of the P already different. Okay, the meaning of P is difference. Okay, now make sure you already know how to interpret. 2.86 control chart will require 2.86 sample to detect the process shift. So just now 140.2. So we will take 2.86 sample, then the process shift might detected. Or in the other word, we will detect the process shift after we have taken 2.86 samples on the average. This word is very, very important, on the average. And then for time interval, h equal to 1 hour, the average time required to detect this shift is, you see, we still calculate ATS, but we use ARL1 multiply H, so which is 2.86 hours. Okay, so we can go to the next. But for me, um, I think it is better to understand, because if you don't understand, then when I move to this example, you still blur. What is that? Don't understand. But once you understand, when we move to others example or we move to other situation, then it's not a problem for you. Okay, let's see whether you understand or you don't understand when we discuss this example. Suppose that this is an unacceptable because production of wafer with mean flow width of 1.725 micron result in excessive scrap cost and can result in further upstream manufacturing problems. How can we reduce the time needed to detect the out of control condition? Okay, this is to detect the out of control condition and then reduce the time. One method is to sample more frequently. Okay, let's see an example. For example, if we sample every hour, half an hour, so the gap, 30 minutes, half an hour, take the sample. Then the average time to signal for this scheme is ATS equal to ARL1 H. So it's 2.86 divided by 2 is 1.43. So only 1.43 hours were elapsed on the average between the shift and its detection. So this is talking about the process shift. The second possibility is to increase the sample size. We use n equal to 10. The probability of X bar falling between the control limit, the process mean is 1.725 micron, is approximately 0.1. So that P is equal to 0.9. Then from the equation 5.2, we can calculate out of control ARL is 1.11. And if we consider the sample, we do the sampling every hours, then the average time to get the out of control signal is 1.11 hours. So the largest of the sample size will allow the shift to be detected more quickly than with the smallest one. So in this slide, talking about the process shift. So in this slide, I have mentioned two ways. Okay, you can have a read, try to understand. you can see the comparison. For sample size n equal to 5, sampling frequent every half an hour. And then for the second design, sample size n equal to 10, sampling frequency every hour. So any difference? So please have a read, understand, and if you are able to write down the summary, you can refer to design 1, design 2. Okay, design 1, design 2 to make a conclusion. Larger sample size, what happened? Or larger sampling frequency, what happened? Okay, actually already in this slide, he already mentioned, but not very clear. So I want you to read through and then give your own conclusion, or you sum up the statement by referring to design 1 and design 2. Yeah, so far any question from you? Yeah, you can see the calculation is quite simple, but I guess, yeah, the calculation is simple, but I guess when I say we need to interpret the value we calculated, maybe for you it's a big problem. Maybe you don't know how to interpret. Just imagine if one day you check your ATM, you press your password, and then you see, right, in your account remain 10 ringgit. But before, they said one day before you check your account, your ATM, you still have, let's say, 500. But today you check your ATM account, remain 10 ringgit. From 500 ringgit reduced to 10 ringgit. So from what we can see here is you lost your money, right? Your money goes somewhere. Don't know where your money go. But because of we only have 10 ringgit in ATM account, then we might say, yeah, I'm so poor. I only have 10 ringgit. So this is regarding to how to interpret the value. Okay, how to interpret the value we calculated by using the equation or by using the formula in sense or in field, in context of quality control. So in our discussion today, so you see calculation simple, but are you able to interpret the value? Interpret the, what you call, ARL, not ARL1. Can you interpret P value, probability value? Okay, so no other thing. Okay, no other thing. Before we can do some interpretation, first we need to know how to calculate. Second, we need to understand the meaning. Okay, we need to understand the meaning of the value we obtain from the calculation. And then we can do the interpretation. We can explain what does the meaning, what is the meaning of the value. So do not think that interpretation is difficult. So actually, we just do the explanation upon the value we obtain. Okay, now, yeah, we still have few minutes to go. Okay, let's go through these rational subgroups. As I mentioned to you, quality control is extension from data analysis, extension from sampling. And it's true because so far we have sample size. So in quality control, when we consider the samples, so there are some of the terms in the sampling. So we have rational subgroups. The rational subgroup concept means that subgroups. So these subgroups or samples should be selected so that if assignable causes are present, chance for differences between subgroups will be maximized, while chance for different due to assignable causes within a subgroup will be minimized. So this is for rational subgroup. Two general approach for constructing rational subgroup. Sample consists of unit produced at the same time. Consecutive unit primary purpose is to detect process shift. Second, sample consists of unit that are representative of all unit produced since last sample. Random sample of all process output over sampling interval. Okay, let's see some figures for the rational subgroup. So they are A, B, A, B. There are two figures. Okay, let's say figure 5.10. The snapshot approach to rational subgroup. A, behavior of the process mean. B, corresponding X bar and R control chart. Okay, A is the behavior of the process mean. Okay, the mean look like this. When we plot the control chart, the upper one is X bar control chart and the lower one is R control chart. And then for the random sample, so we can plot the X bar control chart and R control chart. Okay, so this is the different process, mean, and different control chart we might obtain. And then for the pattern of control chart, I think in the last week we have discussed some of the pattern. Mainly there are three types, right? So this is one of the example of X control chart like this. Pattern is very non-random in appearance. 19 of 25 point plot below the center line, where only 6 point above. So this is referred to figure 5.12 to mention or to discuss how to discuss the figure 1.12. 5 point in a row increase in multiple run up. You see, run up. There is also an unusually long run down begin with 18. Start from 18, so you see the point reduce. So this is how you just read through the sentence, see how to interpret or how to explain the control chart, the point in the control chart. And then for the cyclic pattern, so the cyclic pattern like this. Just now is this one not mentioned, it just mentioned pattern. No specific name. But for cyclic pattern, yeah, you see like this. They have a cycle. And then how about this? You see, we have zoom A, B, C, CBA. You can have a read. 1 point plot outside the 3 sigma control limit. 2 out of 3 consequent point plot beyond. 4 out of 5 consequent point plot 8. This is just to explain what can we see physically from the control chart. And these 4 are the 4 sentences. So in Bahasa, we said this is what you call the surat we can see on ice. This is talking about what we can see on ice from the control chart. We also can talking about what we cannot see from the control chart, but it's related to control chart. The sirat, right? Okay, you have a read for this discussion of the sensitizing rules. There are 10 rules. You can have a read. .4 is the overall type 1 error or 4 alarm probability. So just take 1 minus multiply 1 minus alpha I. So this is to get the overall type 1 error. This one I think I have mentioned to you in quality control. There are two phases, phase 1 and phase 2. Phase 1 is try the control. We plot the control chart. We can say this is the retrospective analysis process. And in the second phase, we use the keyword monitor, or we say the process monitoring. And these are 7 7 tools. I think these 7 tools we have mentioned, we have discussed in the beginning of chapter 3. So you can have a read, see histogram, checklist, how are these two look like. This is the Pareto chart I have mentioned to you. Although this chart do not have any curve line, but actually if we draw a line, so you can have a exponential curve. Okay, from 36 reduced to 1 is a exponential curve line. If we do not put the line, from the histogram also can get the Pareto chart. This is what I meant to you. Pareto chart with the line. This is without line. This is with line. Cause and effect diagram. This is what we call fishbone, right? Fishbone. Ichikawa fishbone diagram. Detailed concentration diagram like this. Scatter plot. I think you are familiar with this scatter plot. And this SPC application we have discussed in chapter 2, the MAIC. Okay, so I think the rest you can have a look. They are all figures and diagram. Okay, so I think I will stop at here. So any question from you before we leave? Yeah, already 10 o'clock. Okay, if no question, we meet again tomorrow. So tomorrow, I think we will go to the next chapter, wearable control chart. So tomorrow class, we will do online classes. We will do online class. So you no need to go to class. So you can stay in your home. So we do online class. So tomorrow we will discuss control chart. Maybe you need to prepare maybe you need to put your laptop aside so that on the spot we can plot the control chart. Okay, if no question, then we meet again tomorrow. So see you tomorrow. Bye bye.
Thank you, sir.
Thank you, doctor.
Thank you, doctor.
Thank you,
Thank you, doctor.
Thank you, doctor.